here, and it's also a pleasure to see that there is a seminar series dedicated to input to state stability, so that there is a renewed interest really in the topic. So this is a work that's started a few years ago now, but still, I don't think that it's very known somehow, but I think it's interesting, and there are interesting directions that one can try to explore in this particular topic. So the title of the talk: Input to State Stability for Complex Dynamics from Global to Almost Global and Back. And so there, let me see if I understand how to change slide here with this pointer. Apparently, yes, like this. So the main motivation here is to try to understand robustness. And you all know input to state stability. It deals with systems which have a single equilibrium, globally asymptotically stable. That's the classical notion. And whereas we would like to really understand robustness in much more general contexts. So for instance, we would like to talk about robustness of very familiar phase portraits, such as the van der Pol oscillator, maybe multi-stable system where you've got two stable equilibria and one unstable equilibrium somewhere, and yet you would like to see what happens under disturbances, or maybe even almost global stability, like in this case, a pendulum phase portrait. When you look at it over the cylinder, one equilibrium is almost globally asymptotically stable, the other is a saddle point, so it only attracts a zero measure set of initial conditions. And yet, what happens when we apply disturbances to such systems? And of course, applications can be in many areas: neuroscience, oscillators, networks, multi-stable system. You have them distributed decision-making systems, biology. You've got chemical switches and stuff like that. And in mechanics, classical mechanics, all your state spaces are going to be non-Euclidean very often, and all of this introduces obstructions to global stabilization. So the best you can do with continuous controllers is maybe almost global stability. So all of these issues will come up in many different areas. And so this is the outline of the talk. I will first of all recall the definition of input to state stability, the classical one. I'll try to go quick here, present some equivalent formulations and applications, and then really talk about possible ways to extend this notion to the context that I would like to deal with. So we'll compare two approaches. One is the global attractivity one versus what we could call the almost global stability one, and provide Lyapunov characterizations and so on. And finally, we talk about decomposition of invariant sets, which is a notion which is instrumental in stating the main results. So you all know comparison functions, of course, positive definite functions. I will make use of this concept: class K, usual stuff, class K infinity, class L, and KL. So since this audience is really focused on input to state stability, I don't think that I need to recall this notion. And so this is just a graphical representation of the main class K infinity, K positive definite, and class L. The classical notion then of input to state stability, as you know, is for systems evolving on Euclidean space. Disturbances also in general maybe in a set of Euclidean space, and the equations are x dot equal f x p then that describe your system, and the stability property demands that what we have is an inequality of the following type. So for all solutions, essentially, we can bound the norm of the solution with the maximum of two terms. One is a KL function of initial conditions and time, and one is a K infinity function of the infinity norm of the disturbance being applied. Okay, so that's the standard property. This is a graphical representation, if you want. So the solution is constrained to live inside this kind of envelope, which shrinks initially maybe and then stays constant as a function of the size of the disturbance. Okay, so this is a nice property, and some of the things that have made this concept so popular are that it's a fairly natural formulation, it turns out it has many equivalent characterizations. And the most important ones, recall it here, is the, for instance, Lyapunov-like characterization. So you can characterize input to state stability by looking at Lyapunov-like dissipation inequalities, where your Lyapunov function is sandwiched in between two K-infinity functions of the state norm, so alpha 1, alpha 2. And what you ask is that, for instance, V dot then is less or equal the minus alpha of the norm of X plus delta of the disturbance D. And in fact, there is different equivalent ways of saying this. For instance, another equivalent way is to actually replace the norm of X with the Lyapunov function itself. And we will see, in fact, that this equivalence will break down in the new setup that we're going to see later. And yes, there are also other types of Lyapunov characterization, but I'm not going to insist on those here. And then another very important characterization, which is one that I will advocate for using in a more general context, is exactly this characterization through asymptotic gains. So what you state here is that the solution for large times should be bounded by a K-infinity norm of D infinity. And this is under very mild additional technical conditions, such as Lyapunov stability of the equilibrium in zero for zero disturbance. This is equivalent to input to state stability. So notice that this property here is a priori very non-uniform. There is no requirement of uniformity in the way things converge to this value, okay? It's just an asymptotic characterization. There's no KL bound, and we don't say how much time it takes to even reach a neighborhood of this gamma, the infinity value. So there's no uniformity in that. This is going to be interesting for later. So then there are also many other results, of course, that you are familiar with, that input to state stability tools have been used in order to deal with interconnected systems. So it's a fairly modular property, so preserved under cascades, small gain results for feed interconnections, and so on. And so all of these perhaps would be interesting to look at in this more general setup as well. So let's now dig into the systems we would like to study, okay? More general dynamics, for instance, very simple equation of a pendulum. I might regard this as a system evolving on a cylinder. So theta is the angle, evolves in a circle, and theta dot is the speed, so it evolves in R. And the problem here is that we don't have, even for the autonomous system, we don't have global asymptotic stability. We have almost global asymptotic stability, okay, because there is a saddle point, which is opposite, of course, to the stable downward pendulum position. And another situation where we would like to understand robustness is, of course, for instance, for this van der Pol oscillator. And we all know that inside a stable limit cycle, well, there's always an equilibrium, okay? In fact, it doesn't matter whether this is stable or unstable, but there is an equilibrium inside. And in the case of the stable limit cycle, there's an unstable focusing point here. So the classical ISS theory cannot be applied. Now, turns out, in fact, that ISS was initially formulated with respect to a single equilibrium, okay, but then was extended with respect to a set. So there is this so-called set ISS that you might be familiar with, which basically replaces everywhere in the definition the notion of norm of X with the notion of distance to the set, whatever you want to call it, that you're considering. Now, in this case, however, you will see that we cannot apply set ISS, because in set ISS, the set is meant to be globally asymptotically stable. So you cannot apply set ISS in here, not if you choose the set to be this equilibrium, but you can't apply it even if you chose the set to be the union of the saddle point and this equilibrium. This is because the part here of the set is not Lyapunov stable, the set as such is not Lyapunov stable. Similarly, for the van der Pol oscillator, you cannot choose your set be the periodic solution, okay? Because you still have something which is not attracted to this periodic solution. And yet, if you include in the set the equilibrium here, again, you lose Lyapunov stability. And so the standard notion of set ISS cannot be applied here. However, there is an alternative approach which is possible to pursue, which is to take what is sometimes called the Milner's attractor. So basically is the set, which is the smallest set, which is globally asymptotically stable. So if you've got van der Pol oscillator, the so-called Milner's attractor is this guy here. So as you can see, it includes the equilibrium, it includes the periodic solution, but it also includes the connecting orbits between the equilibrium and the periodic solution. This set is globally asymptotically stable. And so you can apply all the set ISS theory whenever you put perturbations in this system. However, this approach is not particularly appealing because it's not tight, even in the absence of disturbances, because what it tells you is that, okay, solutions, if D goes to 0, for instance, will converge to W. But we know very well that solutions don't simply converge to W. They might converge to the periodic solution, or we would expect them perhaps to converge to this unstable equilibrium. So there's lots of pieces in this set that we know solutions will not go and let's say asymptotically. And so fattening up the set in this way allows us to apply all the theory that we already have, but it's a cheap solution because it's not tight. It doesn't give us very precise solutions, estimates, let's say. So the other two approaches instead, which are tighter, would be to only look at the set, which is formed by the union of all asymptotically stable, for instance, omega limit set, and relax the concept of global ISS to a notion of almost global ISS, okay? So that's one possibility. So that's relaxing the global nature of input to state stability. The alternative, which is the most recent one that I've been pursuing, however, is the one that basically relaxes the stability requirement of an input to state stability. And basically, we really look at what you could call input to state attractivity, if you like. So we do not insist that our set W should be made only by Lyapunov stable sets, but we are happy to take all essentially omega limit sets, some of which will be Lyapunov stable, others will not be Lyapunov stable, but we will look at an asymptotic gain notion with respect to this set, which is made both by stable and unstable parts. So these are the two somehow complementary approaches. They give complementary information. They also need fairly different techniques to study. And of the two, honestly, this is the one I went for in the past because I was somehow still interested in this almost global notions, and I thought that the stability part was very important. But in fact, it turns out that the global attractivity one is much more natural as an extension to input to state stability, in the sense that the theory really translates with minor modifications in the theorem statements, but huge modifications in the proof. So that's actually quite remarkable. So you will see that.
So David, excuse me, so here one has understood that when you are moving the pointer, then somehow we start to hear you not as good as usual. So maybe...
Is that true? There is delay when I move the pointer. Okay, so I'll stop moving the pointer. I don't really need it much.
Yeah, well, maybe there is some, I mean, connection. Maybe the microphone is very close to that place. I don't know, but...
the microphone is the...
So yeah, we just wanted to say...
If I move it with this thing, is it better?
Maybe.
Because I was using the...
No, it's very bad. It's very bad. Every time you move the pointer, the sound is horrible.
Okay, so it's a weird interference. It's not due to the microphone. Okay, I will avoid moving it then. So here we've got this then notion of asymptotic gain. We take a set W, which contains all the omega limit sets of the autonomous systems. And we say that the system is input to state stable with respect to W if we have that the distance to W, denoted as this norm with the subscript W, in the limb soup is less or equal than a k infinity function of the infinity norm of the disturbance. So that is the usual asymptotic gain notion, where I have replaced the norm of X with the distance to W. And notice that I am not asking for the Lyapunov stability part that was needed in order to have the equivalence between standard ISS and asymptotic gain. Okay, so the Lyapunov stability part will be replaced by some other property that, in the context of the single equilibrium system, will be basically absence of homoclinic cycles. So solutions that sort of start from the equilibrium and go back to the equilibrium. So if you rule out such solutions and you ask for global asymptotic gain, then you have a standard ISS for the single equilibrium case, and it gives also the Lyapunov stability part, okay? But in general, for a set W, we will basically assume that W fulfills a certain property that I will call decomposition without cycles. That is some sort of extension of this notion of not having homoclinic solutions, so solutions that start from W and go back to W in a sense, in a certain sense, but to the same component of W. We have to make clear what this really means. But so we'll say this more precisely later. So with this definition, what we get is this equivalence. So basically, a system is input to state stability with respect to W if W admits a decomposition without cycles, if and only if there exist k infinity functions alpha 1, alpha, and gamma, and the smooth function v of x defined on our state space, which now is a manifold in general M, such that v of x is lower bounded by a k infinity function of the distance to the set W, and v dot, essentially, so the derivative along the solution, the system is less or equal than minus a k infinity function of the distance to W plus, again, gamma of the disturbance D being applied. So this result, as you can see, is really in the same spirit of classical input to state stability. The only difference being that a k infinity function has disappeared. This is not an accident, let's say. So this is intentional because, of course, we all know that if we put back that k-infinity function, that is what we call set ISS. And in fact, it forces the set W to be Lyapunov stable. Okay, so it rules out all the applications that I wanted to deal with. But remarkably, all we need to do is just remove that k-infinity function from the right, and the same theory applies. Okay. By the way, notice here that the dissipation inequality now, it's in the form of alpha norm distance to W, which is not equivalent to having V of X, okay? Because now V of X is not sandwiched in between alpha 1 and alpha 2, so it's not the same as the norm, as the distance to W qualitatively, meaning that the sublevel sets of V don't look like neighborhoods of W. Okay, so there is this is the big difference in this ISS. Somehow the sublevel sets of the Lyapunov functions are not useful in determining where you're going to end up asymptotically, okay? And that's why the proof is quite different. All right. So why did it take 20 years from this classical ISS to this result to actually just erase a k-infinity function from the theorem? So there are a couple of explanations. One is that I started somehow taking the wrong direction. I went almost global first. So I was thinking about these issues, but still took the wrong direction somehow. And the other thing is that the result is somehow sort of new, even for autonomous systems, so systems without disturbances, although it was proved as a Lyapunov theorem for system only on compact manifolds and without disturbances. So there was a version of this Lyapunov theorem. So then the concept of decomposition without cycles, we basically borrowed it from these results, which were dealing with systems on manifolds. And in fact, somehow the results is also non-trivial in both directions. So normally in Lyapunov results, one implication is easier to prove than the converse theorem. But this time, somehow even the forward part of the implication is non-trivial, because there is this difference between the neighborhoods of W and the sublevel set of V. So it's not just based on invariance. So maybe I can very briefly recall the wrong direction that I took at some point. So the alternative approach was to look for almost global asymptotic stability and then almost ISS. So how does one define almost global asymptotic stability? You cannot use KL bounds like this, because due to somehow the stickiness effect, whenever you've got an unstable equilibrium or an unstable invariant set, it takes you forever to get out of it, the closer you get to it. And so you don't expect to have a uniform KL bound that tells you how fast you converge to the origin, say. So you need to basically use a non-uniform asymptotic gain in this context. So you can say that for almost all initial conditions, you converge to the origin. So, and this would be an almost global attractivity property that then you combine with local asymptotic stability, and then that could be almost global, let's say, asymptotic stability. So how to do almost global ISS then? Well, you could again try to have an asymptotic gain property. You cannot make use of KL bounds, we said already. So you could say that for all disturbances, there exists a bed set of measure zero, which potentially depends on the disturbance D, such that if you don't start in the bed set, so for all x0 in your state space N, minus the bad set, you still get this asymptotic gain estimate. Limb soup is less or equal than gamma of the infinity. So the problem is, of course, still how to test this property, because this is now very, very different from the classical ISS property. And to show some of the subtleties of this particular situation, we can take the simplest possible almost global system, a scalar system somehow evolving on the circle, theta dot equal minus n sine theta, in the absence of disturbance. And we put a disturbance d there, additive. So for d equals 0, you have the phase portrait on the left. All solution leave pi and converge towards 0. Whenever you've got a d positive or negative, those two equilibria move to the left or to the right, and still all solution, almost all solution, except for those starting at the equilibria, will go, if d is constant, to the asymptotically stable equilibrium, okay? But then you can start asking, all right, so this is for constant disturbances, but ISS is robustness with respect to time-varying disturbances. So what happens if you start moving d around? You apply, for instance, a square wave, sometimes positive, sometimes negative. As you see, in the upper part of the circle, your solution will move to the right and to the left alternatively, and there is potential for capturing some solutions there, a big interval of solutions, so potentially non-zero measure set, away from the stable equilibrium down there. So it turns out that, in fact, this is not happening in this particular example. And one way to study this is by using density functions. So you basically define a function rho of x, which is C1 everywhere in your state space except at the origin, where you want to converge, and you make sure that its integral is finite as soon as you remove a neighborhood of the origin. And then what you ask is that the divergence of this be, of the product rho x, f of x, be positive. So this means that your volume is expanding almost everywhere, where the volume is measured as integrating the density function over a certain set. And under such conditions, you have almost global attractivity to 0, okay? The idea to convey this theorem that I have is, okay, when you take a toothpaste tube, and that has finite volume, right? Now, instead of the toothpaste expanding, of course, you can squeeze the tube, which is kind of the opposite effect than having it expanding. So you squeeze your tube and all the toothpaste comes up at the only place where the volume is free to expand, is infinite somehow. So almost all the toothpaste will get out of it. So that's the idea, if you like, of density functions and why they're a natural tool somehow to prove almost global attractivity in this case. And it turns out one can try to use those also for ISS. And so what one can ask is that there is expansion of the volume provided x is large with respect to the norm of d. So x bigger than gamma of d implies that the divergence is bigger than 0. So it turns out that this forces everything towards the region where the state is less than gamma d somehow. However, it does so, it turns out, in the sense of the limb inf rather of the limb soup. There is no invariance in this technique embedded, so once you get there, you might get out of it. And so you can only prove a limb inf condition. This is not asymptotic gain, of course, and you need perhaps some primal Lyapunov technique now that you've been able to get out of the region around the unstable equilibrium, you can then apply primal Lyapunov to stay constrained to a neighborhood of the stable equilibrium. So basically, through a combination of primal and dual Lyapunov techniques, one can first of all prove a Lie condition and then use standard Lyapunov to prove a Lie condition. So that was the approach. But as you see, it's very tricky, right? And there are other problems that come up with designing density functions. Finding density functions is not easy at all. And whenever you've got unstable saddle points, it turns out that there's very precise conditions that need to be fulfilled. So in particular, the density function needs to be identically zero on the stable manifold to fulfill such a condition. So that is, while you can prove converse dual Lyapunov theorem, it also makes the hope of finding such density functions quite remote, because you need the shape of the density function to be very, very well tuned with the stable manifold of your saddle points, which means basically you never know what these stable manifolds are. So designing the density function is actually harder sometimes than using other approaches. So we then moved away from density functions and tried to use Lyapunov functions, but maybe exploiting hyperbolicity of equilibria and the permanence of stable and unstable manifolds under small perturbations to prove some kind of sufficient conditions again for input to state stability. So we were able, for instance, to prove almost global input to state stability for a pendulum with friction. And the idea of the result is that we need to know that all equilibria are hyperbolic, and then we need to know that outside of equilibria we've got a strict Lyapunov function and some kind of ultimate boundedness hold. So we have a criteria then, which is stated here as a sufficient condition for almost global ISS, which is again based on standard Lyapunov. And as you see, what we ask is that our Lyapunov function is strict outside of equilibrium, and we've got ultimate boundedness. Notice that ultimate boundedness is not that hard to prove somehow, because you don't need to be tight. You don't need to provide a bound that shrinks to the equilibrium. You can just take a very big set that includes all your omega limit sets. So both, for instance, in the case of the pendulum, the stable and unstable equilibrium, and use standard Lyapunov to prove that standard dissipation inequalities, to prove that you converge to such a bound in the presence of disturbances. And so there are techniques to prove that all of this combined together gives rise to almost global asymptotic input to state stability. So in this case, for instance, if you want to look at this example, you take the pendulum equation, you use the mechanical energy, you derive it, and you can find an upper bound using just a completion of square technique that allows to replace the dissipation, which is in theta dot square. You can replace it with you replace the theta dot d term with a completion of square, so it's minus theta dot square plus d square, and then you replace the theta dot square with w just by noticing that the cosine is a bounded function, and so it's just a 1 that you need to put on the right hand side of that inequality. And that is good enough bound. As you see, it's a scalar ISS-like inequality, except that you don't have a k-infinity function of d, but you've got a function that starts away from 0. Gamma of d in 0, gamma of 0 is not 0. But so you've got ultimate boundedness then proved. And now your Lyapunov function is non-strict, you could say. As you could see, one would need to apply Lasalle somehow to prove global asymptotic stability in that case, almost global asymptotic stability. But you can make it strict just with a perturbation epsilon theta dot sine theta, and it turns out then that you get something that strictly decreases outside of equilibrium. So it's possible to have that. It's not difficult in this example. And of course, your equilibria are hyperbolic, which I said was another assumption. So there's a saddle in pi 0, and there is a node, sorry, a focus in 0, 0. And so you can apply the theorem and you get almost global ISS of the pendulum. So this is quite interesting because it tells us that almost all solutions will converge to a neighborhood of the asymptotically stable equilibrium whose size is proportional to the amplitude of the disturbance. Notice that this is true only for almost all solutions. Okay, there are solutions always typically that will in fact converge to the unstable equilibrium, or to that might converge to the unstable equilibrium somehow, or stay around it. But this is only going to happen for a zero measure set of initial conditions, which is dependent on the disturbance. Okay, so sketch of the proof. It's basically the idea is that for big disturbances, there's nothing to prove, because for big disturbances, we've got ultimate boundedness. So we can tune our K infinity function to be sufficiently big for big disturbances so that we know that we end up in this invariant set. So the only thing we've got to care about are small disturbances. But for sufficiently small disturbances, there are results that give you a persistence of the stable and unstable manifolds of hyperbolic equilibria. So we use that, and so that allows us to say that basically eventually the solutions will stay close to a single equilibrium. This is because we've got strict decrease of V except around equilibrium. And then basically there are two conditions. So we know that solutions eventually are going to be close to a single equilibrium. And if this equilibrium is asymptotically stable, then we have a K infinity bound that applies. If, on the other hand, the solution stays close to an unstable equilibrium, we know that this can only happen for a zero measure set of initial conditions. So it's a kind of pathological solution that we expect only in very special cases. So for almost all solutions, then we go to the asymptotically stable equilibrium. Okay. So back then to global, which this is somehow the chronological order in which our analysis went about this problem. So we started almost global density function, almost global stable manifold theory, and then back to global, relaxing the Lyapunov part of it. And so, as I said, we want to include both stable and unstable omega limit set, but we need additional conditions to guarantee existence of Lyapunov functions. So these additional conditions are quite mild, in fact. So for instance, I've plotted here a phase portrait, okay? And the idea is that whenever you've got omega limit sets, you can somehow multiple omega limit sets, and you've got a union of them, a disjoint union of them. You can kind of associate to your dynamics. This is the dynamics in the absence of disturbances, okay? You can associate an abstract graph that somehow represents how those omega limit sets are connected with each other. So you see from the point, equilibrium point A, you can travel to B. So you can put in the graph, you can put an arrow between A and B. From C also, you can go to B. So there is an arc between C and B, or you could go to D, the limit cycle. Or again, there is another equilibrium E that can go to D. So in this particular example, as you can see, the graph somehow associated to the dynamic doesn't have cycles. And that's what guarantees that you can find basically a Lyapunov function that is strict outside the omega limit sets. okay, the lack of these cycles in the associated graph. So despite only having a attractivity property, you can have a converse Lyapunov theorem for this situation. And this is a fairly general assumption, honestly. It holds for many, many examples of interest, like such as van der Pol oscillators or pendulum, or with friction or multi-stable systems. They all have phase portraits which have a graph associated to them, which has no cycles. It's in fact rather simple graph. So all of these examples admit a decomposition without cycles. So not admitting a decompositions are systems such as system with homoclinic trajectories or system with heteroclinic loops, also between non-trivial attractors, okay? And by the way, they do not admit a decomposition where you take as atoms of your decomposition the individual omega limit sets. But in fact, if you're happy to take all the cycles, so the interconnecting orbits between them as your new atom, eventually you can find a coarse enough decomposition that will in fact kill somehow the cycle. So you will be able to have no cycles, okay? And so then you can apply that particular situation, your converse Lyapunov theorem, that was the one I stated before. So now, it turns out this approach, I've presented it for input to state stability. Turns out it can be done also with integral ISS. Integral ISS does not have an asymptotic gain property, but it has bounded energy, bounded state properties, so which kind of play the same role of asymptotic gain. So you can formulate things in that setup again. And you could look then also maybe at detectability properties within this framework. Something has been done. And you can look at interconnections. We also started doing this. We've done cascades. We haven't really looked at feedback loops. This theory is really quite general, I think. It could be maybe even extended to hybrid systems, okay? So because it's global, it's fully compatible with the ISS theory that you're familiar with. We've got all the compactness that we need. We don't have almost global situations that kind of kill the topology things. And it's also, yeah, very flexible. All we need is this decomposition without cycles. That's the main ingredient, technical ingredient that you can take, and that will allow you to extend things in many different domains. And then, of course, the potential for applications in many areas are also a lot, I think. So that's all I wanted to tell you about, and I will thank some of the co-authors with whom I've done this work, Dennis Asymptotic for the global stuff, and Laurent Perly for the manifolds, and of course Eduardo, who's brought me into the field. And that's all. Thanks for listening.